Good afternoon, class. Here's chapter 3, derivatives, section 3.7, derivatives of the logarithmic functions. We've already covered derivatives and rates of change. The derivatives as a function. The two sections use definitions. We added basic differentiation formulas, the product and quotient rules, the chain rule, and we are going to go over derivatives of a log functions. This is the synopsis of that. We will elaborate on those in a moment. Reminding everyone of differentiation formulas, starting with the definition. Basic differentiation such as the power rule, exponential functions, trigonometric functions, the product rule, the quotient rule, the chain rule, exponential rules. We are adding logarithmic rules as well. So to start with, I'm going to remind you of logs and its properties. If a b is positive and b can't be 1, it's not equal to 1, then y equals log x base b is equivalent to x equals b to the power 1. What I want to do is to remind you of everything you have studied before in algebra, intermediate algebra, college algebra, and then pre-calculus. If you look at this case, x is b to the power of y, that means y equals log x base b. In both cases, we have the same exponent, and in both cases, we have the same base. 2, make sure we understand this. If you look at the method that I'm going to use here, log x base b of y, of base b equals y, if you go with this arrow that I'm showing you, b to the power of y becomes x. If you can go from logarithmic format to exponential format and back, then you have no problem with all the properties we're going to discuss. And so what you really need to know, log is simply an exponent. So for example, if somebody says, what is log 8 when the base is 2? This question is asked. It's the same as asking 2 to what power is 8? Both of them have the same answer, 3. Then it gives rise to the following properties. Okay, again, knowing how to go from one format to the next. Log of 1 with any base is 0. Notice if you go with this arrow, b to the power of 0 is 1. Log of b base b equals 1. Again, b to the power of 1 is b, which says if the argument of log, this is the argument, this is the base. If the argument of log is identical to the base, the answer is 1. This one, b to the power of x, is b to the power of x. This one, b to the power of log x base b equals to x. And these two properties together refer to the fact that logarithmic functions and exponential functions are inverse functions, and I can't emphasize this enough. Now, this is called the product rule. Log of x y base b equals log x base b plus log y base b. Log of x over y base b is log of x base b minus log of y base b. This is the quotient rule. And log of x to the power of n base b is n log of x base b. That means the exponent becomes the coefficient known as the power rule. Now, if we change the base to number 10, we don't write that and the name is common log. So anytime you see log missing the base, that means the base is 10. And this means 10 to the power of y equals x, which gives rise to the following properties. Again, this is a general case, this is a specific case. So log 1 is 0. You don't have to write the base. Log 10 equals 1. Why is that? Remember, when the base and the argument are the same, the answer is 1. The base is missing, that means the base is 10. So log of 10 equals 1. Again, these two, just like these two, show that logarithmic functions and exponential functions are inverse of each other. 5, the product rule, number 6, the quotient rule, number 7, the power rule. We write the same thing, but without the base. If there is no base, the base is 10, known as common law. Now, if we use the base e, log x base e, then we don't use log, we use ln. This is a natural log. So the moment we see y equals ln x, we know the base is e, and therefore e to the power of y equals to x, giving rise to these properties from the general form. Again, ln 1 equal to 0. Why is this ln e? Because when you write ln, you know the base is e, they must be identical according to this, and therefore ln equals to 1. The same thing here, the base must be the same, so it's e. These two again refer to the fact that logarithmic functions of any kind with their appropriate exponential functions are inverse functions. This is the product rule, the quotient rule, the power rule, and in each and every one of them, we just use ln. And here's the graph of y equals e to the power of x versus the graph of y equals ln x in the same set of axes. Because they are inverse functions, they must be symmetric with respect to the line y equals x. We also looked at, in algebra, change of base formula. If log x has base b, we can say it's log x over log b, and we choose any base. In this case, when we write a, that means a general case. In this case, when we have the missing base, that means common log, so the base is 10. When we use ln, meaning the base is e, normally we use one of those two, and the reason being is because we want to make sure that we can handle it, because sometimes you want to calculate this and the calculators can't. I want to refresh your memory about this basics, and so we are going to go over some of the questions we've seen in elementary algebra, in intermediate algebra. So log 81 base 3, we want to figure out several ways of looking at it. First of all, you notice this is 4 because you know 3 to the power of 4 is 81. If you go this route, it's absolutely fine. However, we could actually work it out in the following manner, and we write log base 3 of 81. I don't know what the answer is, so I'm going to call it x. And now by definition, I'm going to write 3 to the power of x is 81. I know 81 is 3 to the power of 4, so x must be 4. This is what we did when we started doing the logs in algebra. The second one, log 5 base 25, or log to the base of 25 of 5, or log base 25 of 5. You have to mention the word base somewhere. What is that? It's equal to 1/2. Why is that? Again, if you go with the arrow, because 25 to the power of 1/2, or square root of 25, is 5. If we want to justify it just the way we did the other one, we are going to write log base 25 of 5 is missing. This time, let me use a different variable, y. Then by definition, 25 to the power of y must be 5. We know 25 can be replaced by 5 squared. So 5 to the power of 2x is equal to 5. And the 5 with no exponent means the exponent is 1. 2x must be 1 and x equals 1/2. So you could prove it this way and you're done. The next one, the answer is -3. Why is that? Because 0.001 is 10 to the power of -3. And if you replace this with 10 to the power of -3, simply by one of the properties that was mentioned, known as the power rule, the answer becomes -3. What I want to remind you is the following, everybody. When you're dealing with common logs, log of 10 equals 1, log of 100 is 2, log of, let's say, 100,000 is 5. Log of 0.1 is -1. Log of 0.02 was -2. Log of, let's say, 0.000. This is 1, everybody. 1 is -4. Meaning, when you're dealing with powers of 10, number of zeros will give you the answer. There's 1 0 here, +1. 2 zeros here, +2. 1, 2, 3, 4, 5 zeros here is 5. Now, the number of decimals will negate the value. So 1 decimal, -1. 1, 2 decimals, -2. 1, 2, 3, 4 decimals, -4. So this is what we did previously in algebra when we started it. And I wanted to remind you because we are going to use logarithmic properties to do differentiations. We are going to move on. All right, we want to write each and every one of them in an exponential format. And again, I'm going to remind you of this arrow here. So simply put, log 625 base 5 equals 4 is equivalent to 5 to the power of 4 is 625. What about the next one? Log of 49 base 7 equals 2. Equivalently, 7 squared is 49. What about the next one? Log of 81 base 1/3 equals -4. One-third to the power of -4 must be 81. What about log 3 base 81 equals 1/4? 81 to the power of 1/4 must be 3. What about the last one? Log base 1/2 of 32 equals -5. I just wanted to mention it slightly differently. As long as the word base is mentioned, that works out. So that means 1/2 to the power of negative 5 must be 32. So I hope it's clear to everybody. It's very straightforward, everyone. Just knowing the properties of logs will do the job. Let's go to calculus and start differentiating. Y equals ln x. What is the derivative of that? We don't know yet. So we are going to rewrite this in its exponential format, e to the power of y equals x. And now we are going to differentiate both sides implicitly. The derivative of any exponential is itself. So it's e to the power of y times the derivative of y is y prime or dy dx. The right side is x. The answer is 1. So please understand, you can treat y as g of x. So e to the power of g of x is e to the power of g of x times g prime of x, or in this case, y prime. We are going to divide both sides by e to the power of y. And we are going to replace that with x. The answer is 1 over x. So we proved for y equals ln x, the derivative is 1 over x. What does it mean? Flip it over. Write its reciprocal. That's all you have to do. So if we want to expand this concept, so the derivative of ln x in an absolute value is 1 over x. X can't be 0. I'll go over the explanation of that in a moment. If it's g of x, you flip it over. And the reason you write g prime of x, this is by the chain rule. Remember, when we say u is normally a function of x. So if it's ln u, 1 over u times du dx, then we write u is larger than equal to 0, or we have an absolute value x not equal to 0. And the reason why, because as you recall, from the graph of y equals ln x, the domain is what? 0 to infinity. 0 is not included. That's why you may use an absolute value, especially for the reverse process, which will be discussed later on. Or in this case, if you don't want to use that, you say u is larger than or equal to 0. That's the reason it's been used in this fashion. Okay, everyone. All right, we are going to move on, and we are going to look at some examples of logarithmic functions and their derivatives. Okay, so let's do that. We want to differentiate this case. Again, it's very straightforward, everybody. According to the rule that was just discussed, what do? We just flip this over. 1 over 5x minus 1. And then we need its derivative. The derivative of the argument of log, this is called the argument of log, is just 5. And then we rewrite it. That's all you have to do, class. That's all you have to do. Now, we want to differentiate this, and there are 2 ways to approach this. And I'm going to go both ways. Okay. First, I'm going to simply flip this over, everybody. I'm going to flip this over. So I get 1 over x cubed. So I'm looking at this. So anytime I'm differentiating, I write the formulas for me and I follow it, instead of keep on writing ddx of this, ddx of that, which becomes sometimes confusing. So I'm going to write this. So I'm going to flip this over. So I need g prime of x. Remember, I need the derivative of this guy, x cubed, which is 3x squared. And of course, combination of the two results in simply 3 over x, and you're done. 3 over x, and you're done. Right, everybody? 3 over x, and you're done. Now, and you're done. And there is a second method, okay, and that requires knowledge of logs. And in this case, it doesn't make any difference. I can simplify this by using the power rule and put the 3 in front. And now when I want to differentiate, basically I'm dealing with ln x, because 3 remains, and then ln x simply gives me 1 over x, and the result is 3 over x. Now, so I used first algebra. I first used the logarithmic properties to simplify this, and then I used calculus. Now, in this case, it really doesn't make much of a difference, because the question is not that involved. But the more involved the question, the better the second method. For example, we want to differentiate this. If we want to go with the derivative right away, we have to flip this over, which is not a big deal, just, the reciprocal of that. But to differentiate this, now I have to use the quotient rule, and it does take a little bit of a time. So let's go with the easy way out. And this is ln of the top minus ln of the bottom, according to the product rule, quotient rule, my apologies. Now, this one itself, using the product rule, I mean, you can continue with that, but I like to decompose this completely, which means this becomes ln2 plus ln x. So when I want to differentiate, it becomes a lot easier. Number one, this is a number, everybody. So the derivative of ln2 is just 0. So I deal with ln x. So its derivative is 1 over x. And again, just reminding you that the derivative of this guy gives you 0. So you write 0 plus 1 over x. I didn't want to write that, but just in case. Now minus, now we're going to take a derivative of this one. We're going to flip it over as 1 over 2x plus 1. And then by the chain rule, I need the derivative of the inside, which is 2. And now I'm done with calculus. I'm going to box this with an asterisk next to it and tell you that this is it. Calculus is finished. Algebra and more algebra is coming. You want to combine them, you take the LCD, and the least common denominator is the product of the two denominators, x times 2x plus 1. So this one is 1 times 2x plus 1. This one is minus 2 times x. So again, 1 times 2x plus 1 minus a 2 times x. It's, again, very straightforward, everybody. There's really not much to it. All you have to do is simplify the numerator and you're done. Let's do that. This is 2x plus 1 minus 2x. I can get rid of these 2, and the numerator becomes just 1. And we are done, everybody. you're going to move on. All right, I want to differentiate this, and I can do the product rule by noticing that this is 5x times ln x squared, and that works perfectly, still not too bad. However, this one class, I can use the logarithmic properties and write it as 2 ln x. It makes it easier. And now 2 and 5, the product is 10. And now I have 10x times ln x. And now I'm going to use the product rule. I'm going to call this f times g. And I'm going to use the product rule on that, which means f prime, which is the 10 times g ln x, plus g prime, that means 1 over x times f, which is 10x. And clearly, this one will become 10. I can factor the 10 out, and I'm done. Meaning, again, this with the asterisk is the only calculus step, everybody. It's the only calculus step. What about this one? I'm going to write this as f over g. And I'm going to use the quotient rule on that. Therefore, I need f prime g. So f prime is 1 over x times g, which is x, minus I need g prime f. G is x, g prime is 1 times ln x over g squared. That means put this in and square it. So x squared. And again, we are done with calculus here. Now notice the product of these two is simply 1. And so 1 minus ln x over x squared. So again, very straightforward, everybody. So we are dealing with logs and their derivatives, and in some instances, makes a perfect sense to use logarithmic properties to simplify before we move on. Here's another example. If I want to differentiate this just without the properties of logs, I have to flip this over, not a big deal. And then I'm going to differentiate that. That does take some time, okay? And it's a lot easier if I decompose the log first. Anybody knows the decomposition of this? Can anybody want to share with us their answer? So in other words, never mind the calculus part yet. We want to decompose that. What do we get? Anyone? This is, I'm going to do it in 2 steps, although it can be done in 1. It's ln of 3x plus ln of x plus 4 to the power of 5. So ln of this part plus ln of this part, we are using number 5, the product rule. Now, remember what we did with ln 2x? We're going to do the same thing. We're going to cut this into two pieces, ln 3 plus ln x. What about this one? You look at the power rule, I put the 5 in front. So this is completely decomposed as ln 3 plus ln x plus 5 ln of x plus 4. So you decompose the log. This one is a number. ln 3 is a number. The derivative is 0. We don't have to worry about it. ln x, 1 over x. Again, ln 3. If I were to write this, I would write this gives me 0 plus 1 over x. I want to differentiate this. So first I have number 5. It's a coefficient. It's a multiplier. I keep it. Then I have a natural log. I'm going to flip this over. I'm going to write the reciprocal as 1 over x plus 4. And then by the chain rule, I need the derivative of the inside, the derivative of the parentheses, okay, or the argument of log, and it's just 1. The reason I emphasize writing that, because what if it were something else, okay? For example, if it was 2x would be 2. So you want to write that for emphasis. So we're done with calculus. Now, algebraically, we want to take a common denominator, which is simply x times x plus 4, and add them up. So this is 1 over x, so 1 times x plus 4. And this one, the numerator class 5, 1, 1, the numerator is just 5. So 5 times x. So 1 times x plus 4, 5 times x. 5 times x. I can't really emphasize this enough. I hope everybody is okay with that. Just 5. That's all. Okay, it's important to know that. 5 times. So all we have to do is simplify the numerator, and let's do that. This is x plus 4 plus 5x. We can combine x and 5x into 6x and write 6x plus 4 over x times x plus 4. We are done. Couple of things I want to mention, class. Number 1, you don't have to multiply these two. Number 2, if you take the common factor of 2 out or not, it doesn't make any difference. The reason we rather have the denominator in the form of a factored format is because if something cancels out from the top and the bottom. So if you take the 2 out, you get 3x plus 2 and nothing cancels out. All right, we want to differentiate y equals e to the power of 2x times ln x, and gonna start putting a raised dot in between. In other words, we are going to use the product rule. So I'm going to write the product rule and I follow it. So I need f prime g plus g prime f. So let me call e to the power of 2x as the f function, ln x as the g function. So it becomes clear we are using the product rule. So f prime, any exponential, closed eyes, the answer is itself. You look at the exponent is x. No, the exponent is a function of x. You need the derivative of that times 2. The base is e, so we are fine, times g, which is ln x, and then plus g prime, the derivative is 1 over x, times f, which is e to the power of 2x. Again, very straightforward, everybody. So we're done with calculus. We notice that these two statements, they have e to the power of 2x in common. If I take it out, this gives me 2 ln x. This gives me just 1 over x. And that's the final answer. So e to the power of 2x times 2 ln x plus 1 over x. All right.
Hey, Daddy, can you call Mommy?
So we're going to continue differentiating, and we are dealing with y equals log base 3 of square root of x, log base 3 of square root of x. So what we looked at was natural log, and the base was e, but we haven't looked at different bases, so let's see how we deal with that. So let's go over the following. If we have a log with any other base, we're going to use the change of base formula with the natural log. So we're going to write this as ln x over ln b. Please understand ln b is a number. Okay, so ln x divided by ln b. So we're going to write this as 1 over ln b times ln x. 1 over ln b times ln x. This we know how to handle. 1 over ln b is a number, so that remains unchanged. So if I want to differentiate this, this part is a number. So that remains the same. Ln x is 1 over x. So again, what is y prime? This one doesn't change. This one will flip over, becomes 1 over x. And so we write it in this fashion. We say y prime is 1 over x ln b. So that's what we are going to do here. Before we do that, I'm going to write the x as x to the power of 1/2, everybody. So I'm going to change this to x to the power of 1/2. And I'm going to use the power rule, and I put the 1/2 in front. Remember, anytime you're dealing with logs, you want to decompose them first. So I want to differentiate this. The 1/2 is going to remain. Then whatever the argument is, I'm going to flip it over. So the argument is x. I'm going to get 1 over x. Then I notice the base is not e. The base is not e. So I need 1 over ln b, 1 over ln 3. This is because the base is not e. So this takes care of that. And now the final answer, we rewrite it in this fashion, that y prime is 1 over 2x ln 3. Okay, everybody, this is the methodology that we are going to write this. If you recall, in the form of when it was in the form of an exponential, when we were differentiating, we would multiply by ln b if the base wasn't e. Now we divide by the reverse process. We want to differentiate this, and now we notice the only difference when we compare these two is that this was just x, now it's a function of x, and I hope you realize it's really the same answer. We tag along by the chain rule, the derivative of the argument. In other words, what is the derivative of this case? First, 1 over f of x, then times the derivative of f of x, or f prime, by the chain rule. And then because the base is not e, 1 over ln b. And this is the one I'm going to use. Of course, if we put them together, we get 1 over f of x ln b times f prime of x, or put the f prime of x at top. It's the same thing. So this I want to decompose. There is nothing I can do. It is decomposed. It is as simple as it comes. So flip it over, 1 over x squared plus 1. The chain rule says I need the derivative of the parentheses or the argument. So I need times 2x. I look at the base. Is the base e? No. Therefore, I need 1 over ln b. I need 1 over ln 5. And I rewrite the whole thing as 2x over the product of these two pieces. The reason I put x squared plus 1 before ln 5, not after that, Because if you put it after 5, one may think it's ln of 5 times x squared plus 1. So put x squared plus 1 in front, just to be on the safe side, everybody. We want to differentiate y equals ln of sine x. So according to this, just flip it over, 1 over sine x. Flip it over. Then we need g prime. We need the derivative of sine class, which is cosine. And I hope you know cosine x over sine x is cotangent x. Cotangent x. Okay. And again, pretty straightforward, everybody. Y is 1/2 ln of 1 plus x over 1 minus x. And definitely I want to decompose that. If you don't do that, class, so 1/2 remains. This is the number and just carries. But if you want to differentiate it the way it is, you have to flip this over, which becomes 1 minus x over 1 plus x. Then you need to use the quotient rule on that. You don't want that. It becomes very complicated. So we are going to keep the 1/2, and this is ln of the top minus ln of the bottom, meaning I am using this quotient rule, everybody, number 6. Ln of the top minus ln of the bottom. Now I'm ready to differentiate, so I'm going to call it y prime. And the 1/2 doesn't go away. So I'm going to carry the 1/2. Now what happens to this one? Flips over. 1 over 1 plus x times the derivative of the inside by the chain rule is just 1. So even if you don't write it, works, but it's a good practice that you write it so you remind yourself what you need to do, especially now for the second case, because it does make a huge difference, everybody, if we make a mistake. Okay, so in the second case, minus, flip this over, 1 over 1 minus x. And then the derivative of the inside, I hope you see it's minus 1. So times minus 1. And that's why you want to write this. I can't emphasize this enough. Again, I'm going to just put it in a box, put an asterisk next to it. I'm done with calculus class. The rest are all algebra. So I'm going to keep the 1/2, and I'm going to put these two together, which means I want to find the LCD, which is simply the product of these two, 1 plus x, 1 minus x. There's really not much we have to do. So 1 plus x times 1 minus x. So this thing is 1. 1 times 1 minus x. And then this thing is plus 1. Please understand this is plus 1 times 1 plus x. Okay. So 1 times 1 minus x. And then plus 1 times 1 plus x. Okay. And I'm going to continue with the algebra and write 1 minus x plus 1 plus x. And I hope you see that this whole thing becomes just number 2. Everything becomes number 2. Number 2 and 1/2 cancel each other. And it becomes 1 over 1 plus x times 1 minus x. 1 plus x times 1 minus x is 1 minus x squared. Quite a few steps of algebra, class, okay? But it's very straightforward. I want to try this again. Ln of 5x. I want you to see what happens here and what it is. This whole thing itself, and I put asterisk, is your argument. So the argument of the original log is the whole thing. So 1 over that. Now I need the derivative of this. So how do I take the derivative of ln of 5x? 1 over 5x. And then time its derivative 5. So I hope you see how we are making this work. It's very straightforward, everybody. Now putting it together, we have the following because this 5 cancels out the 5. The numerator is 1 times 1. And the bottom is ln 5x times x, and you put the x in front. You put the x in front because otherwise it's awkward.